Andromeda is the largest galaxy in our closest cosmic neighborhood, visible even to the naked eye from dark places on Earth. On quiet, moonless nights, far from city lights, it appears as a faint, elongated glow in the sky, a distant island of stars silently drifting through space. It lies approximately 2.5 million light-years away and is a spiral galaxy, remarkably similar in shape and structure to our own Milky Way. Its immense size and relative closeness have made Andromeda one of the most important objects of astronomical study for centuries. If you are listening to this story to relax before sleep, take a slow, deep breath. Allow your shoulders to soften, and let your thoughts gently drift outward, beyond the Earth, beyond the familiar sky. And if you enjoy these calm scientific journeys, don't forget to support the channel with a like and a subscription. It truly helps keep these quiet explorations of the universe alive for you. For a very long time, humanity believed that the entire universe was limited to the Milky Way alone. Stars, nebulae, and faint clouds of light were all thought to exist within our own galactic home. Only at the beginning of the 20th century did astronomer Edwin Hubble prove that the Andromeda Nebula was, in fact, a completely separate galaxy, a vast system made up of billions of stars, existing far beyond the boundaries of the Milky Way. This discovery became a true scientific revolution. For the first time, it was confirmed that the universe is far larger, deeper, and more complex than anyone had ever imagined. Modern research suggests that Andromeda may contain up to 1 trillion stars, making it roughly twice as massive as the Milky Way. Yet scientists are fascinated not only by the number of stars, but by the galaxy's intricate structure. Andromeda possesses clearly defined spiral arms, a dense and luminous central core, and an enormous halo filled with dark matter, invisible, silent, yet essential. Though we cannot see dark matter directly, it plays a crucial role in holding the galaxy together, binding its vast mass into a single seeable system. Special attention is given to Andromeda's core. At its center, astronomers believe, lies a supermassive black hole with a mass hundreds of millions of times greater than that of our Sun. This black hole governs the motion of nearby stars and may be a source of powerful, high-energy radiation. When compared to the center of the Milky Way, which also hosts a supermassive black hole, Andromeda's appears to have been far more active in the distant past, leaving traces of its influence on a truly cosmic scale. Scientists have also discovered what they poetically call hidden pathways within Andromeda's structure. These are not tunnels in the literal sense, but vast stellar streams, remnants of smaller galaxies that were once torn apart and absorbed by Andromeda's immense gravity. Through spectroscopic observations, astronomers have detected long, delicate threads of stars stretching deep into Andromeda's halo. These stellar rivers are the remains of dwarf galaxies, slowly dismantled and woven into the larger spiral. In this way, Andromeda has rebuilt itself many times throughout its history, growing, evolving, and reshaping its identity by absorbing smaller cosmic systems. When scientists speak of technology in this context, they do not mean artificial machines or alien artifacts. Instead, they refer to the natural technologies of the universe itself, the elegant, physical mechanisms that shape galaxies and stars. One such universal technology is star formation. Within Andromeda's spiral arms, there are active regions where new stars are constantly being born. These regions resemble vast cosmic factories, where clouds of gas and dust slowly collapse, ignite, and transform into brilliant stellar giants. By observing these processes, scientists gain insight into our own distant past. It was through similar processes, billions of years ago, that the stars were formed, stars around which planets would later emerge. Human imagination has also woven legends around Andromeda. In ancient Greek mythology, the galaxy's name is linked to Princess Andromeda, daughter of King Cepheus and Queen Cassiopeia, who was saved from a sea monster by the hero Perseus. Since those ancient times, people have filled the night sky with symbols, stories, and meaning. And although today we study Andromeda as a scientific object, in cultural memory, it remains connected to mystery, myth, and wonder. One of the most fascinating questions concerns Andromeda's future. According to astronomers, in several billion years, Andromeda will collide with the Milky Way. This event will not result in stars crashing into one another. The distances between them are far too vast, but the structures of both galaxies will be dramatically reshaped. Over time, they will merge into a single enormous galaxy, sometimes referred to as Milkomeda or Milky Andromeda. Thus, the story of Andromeda is a story of cosmic construction, of hidden processes, immense timescales, and hypotheses that reflect both the laws of physics and the imagination of humanity. Each new discovery reminds us that we do not live in an isolated world, but within a deeply interconnected cosmic system where the destinies of galaxies intertwine over billions of years. Andromeda has long been the subject of detailed observation, and its study helps us better understand not only spiral galaxies, but the fundamental processes driving the evolution of the universe itself. In brightness and size, it is the largest galaxy in our local group, which includes the Milky Way, the Triangulum Galaxy, and more than 50 dwarf satellite galaxies. Now, imagine a cosmic map unfolding before you, and at its center, Andromeda shines softly, a distant landmark in the quiet ocean of space, guiding our gaze far beyond the familiar stars. Before we dive deeper into its mysteries, gently remind yourself to support the channel ASMR Dreams with a like and a subscription. Your quiet support helps these soothing scientific journeys continue, night after night. According to modern telescope data, the diameter of the Andromeda Galaxy reaches approximately 220,000 light-years, which is almost twice the size of our Milky Way. Its total mass is estimated at around 1.5 trillion solar masses, and a significant portion of this weight belongs to invisible dark matter. It is dark matter that forms the gravitational framework of the galaxy, an unseen structure that holds stars, gas, and cosmic dust in place. Although dark matter does not emit light and does not interact with electromagnetic waves, its presence is revealed through the motion of stars and the rotation speed of the galaxy itself. What is especially fascinating is that Andromeda's structure preserves traces of numerous cosmic construction events. Astronomers have noticed that its spiral arms are uneven and, in some regions, clearly distorted. The reason for this lies in the galaxy's turbulent past. Over billions of years, Andromeda has absorbed dozens of smaller dwarf galaxies. These vast acts of cosmic growth have left behind visible signatures, long streams of stars, and scattered clusters, stretching far beyond the galactic disk. In essence, what we are observing is an archive of ancient cosmic collisions, frozen into a delicate pattern of starlight. Particular attention is drawn to Andromeda's two bright satellite galaxies, M32 and M110. They orbit their massive neighbor and are slowly being torn apart by its immense gravity. Their stars and gas gradually flow into Andromeda's main body, replenishing it with new material. This process resembles construction materials being added to an expanding structure, but on the scale of the universe itself. It offers us a living example of how large galaxies grow by merging with smaller ones. Some hypotheses suggest that Andromeda's central core may contain not one, but two supermassive black holes, currently in the process of merging. This idea arose from observations of unusual stellar motions near the galaxy's center. If this hypothesis is correct, humanity may one day witness an exceptionally rare cosmic event, the union of two colossal black holes. Such a merger would release an enormous amount of energy in the form of gravitational waves, rippling through the fabric of spacetime. For astronomy, this would be an extraordinary opportunity to observe fundamental cosmic processes as they unfold. Legends and myths associated with Andromeda find an unexpected reflection within modern science. In ancient times, people linked strange glowing patches in the night sky to mythical figures and divine stories. Today, we know these are not clouds or simple star clusters, but entire galaxies, vast, complex worlds of their own. Yet the parallels remain. For ancient cultures, Andromeda symbolized sacrifice and salvation. For us, it tells a story of cosmic collisions, destruction, and rebirth. The technologies employed by the universe itself are also revealed through Andromeda's dynamics. One of the most intriguing processes is resonant stellar interaction. As the galaxy rotates, stars can gather into denser regions, forming spiral patterns. These structures are not fixed or permanent. They emerge, dissolve, and reshape under the influence of gravity, creating the illusion of a stable design. In reality, the galaxy is constantly reorganizing itself, like a colossal machine that never stops working, quietly adjusting its form across unimaginable spans of time. There is also a hypothesis suggesting that Andromeda may once have been an elliptical galaxy, later transforming into a spiral as a result of multiple mergers. This idea is based on the distribution of stars and the unique properties of its halo. If this is true, then Andromeda stands before us as a striking example of cosmic transformation, a galaxy that changed its very identity through billions of years of evolution. Thus, every new detail uncovered in the study of Andromeda opens hidden corridors of its history. Its growth occurred through absorption, fusion, and internal restructuring, making it a living witness to the way the universe evolves. For us, Andromeda also offers a glimpse into the future of the Milky Way. One day, our galaxy and Andromeda will merge into a single vast cosmic world. Andromeda is fascinating not only as the closest object for astronomical observation, but as a key to understanding the processes that shape galaxies throughout the universe. Within its structure lie countless clues about how stellar systems are born, evolve, and eventually fade. This is why Andromeda has become a kind of cosmic laboratory, a place where the fundamental laws of the universe reveal themselves. Before we move deeper into the details, gently support this lecture with a like and a subscription, so this scientific project can continue bringing new discoveries into the quiet hours of the night. One of the most impressive discoveries in Andromeda has been the detection of what astronomers call stellar streams. These long, elongated formations are made of stars torn away from smaller galaxies that were destroyed by the gravity of the giant spiral. Astronomers discovered these stellar streams through deep photometric observations and detailed computer simulations. Their shapes and positions reveal that Andromeda has repeatedly absorbed its companions, leaving behind distinct traces in space. Each of these streams can be seen as a hidden passage, leading us back to ancient cosmic catastrophes. For example, one of the most thoroughly studied streams is a gigantic arc of stars stretching hundreds of thousands of light years away from the galactic center. Its analysis showed that it was formed after a collision with a dwarf galaxy approximately 2 billion years ago. In this sense, Andromeda is not simply a single galaxy, but the result of countless mergers and internal reconstructions, a vast cosmic mosaic assembled over immense spans of time. Another important aspect is gas clouds. Surrounding Andromeda is an enormous halo of hot gas, extending hundreds of thousands of light years into space. This halo is so massive that it may contain up to half of the total mass of stars within the galaxy itself. Scientists believe that such gas clouds act as a reservoir for future star formation. Under the right conditions, denser regions can condense within this gas, giving birth to new stars. In this way, the fate of the galaxy is directly linked to its ability to access and utilize this invisible reserve. Special attention is also given to the rotation speed of Andromeda. Observations show that its outer regions rotate faster than would be expected based solely on the visible mass of stars and gas. This discrepancy became one of the strongest pieces of evidence for the existence of dark matter. In reality, the motion of stars within Andromeda demonstrates that without this unseen gravitational framework, the galaxy would simply fall apart. It was precisely such observations that helped scientists understand that dark matter is a universal component of the structure of the universe. Hypotheses about Andromeda's past also include theories about its very origins. According to current models, the first protostellar clouds began forming more than 10 billion years ago. Gradually, these clouds merged, creating larger and larger structures. Over billions of years, a full spiral galaxy emerged, one that has continued to evolve ever since. Some researchers suggest that in its distant past, Andromeda may have been even more active than the Milky Way, forming stars at a much faster rate. This intense period of growth may explain its greater mass and brighter central region. The topic of supernovae in Andromeda is equally fascinating. Historical records describe several stellar explosions that were visible from Earth with the naked eye. In ancient times, people interpreted these sudden lights as omens or signs of fate. Today, we understand that supernovae are a natural stage in the life cycle of massive stars. These powerful explosions not only destroy the stars themselves, but also enrich interstellar space with heavy elements, the building blocks for new planets and, potentially, for life itself. Andromeda has also become a subject in the search for exoplanets. Although we currently lack direct confirmation of planetary systems there due to the immense distance, scientists are confident that with such a vast number of stars, the probability of planets is extraordinarily high. Mathematical models suggest that Andromeda may host millions of Earth-like worlds. And while we cannot yet study them directly, the very possibility expands our understanding of the scale and diversity of life in the universe. Thus, the study of Andromeda reveals its hidden pathways, from stellar streams to vast gas halos. Its story reminds us that galaxies are dynamic systems, constantly reshaping themselves. For us, Andromeda is a window into both the past and the future of the cosmos, where every star and every structure carries traces of an evolution lasting billions of years. One of the most impressive features of the Andromeda galaxy is its central core. It is striking not only because of its size and brightness, but also because it holds crucial clues to understanding the evolution of galaxies like our own. Andromeda's core is twice as bright as the core of the Milky Way. This is linked to the high density of stars and the intense activity in its central region. Before we go deeper into this topic, gently remember to support the channel with a like and a subscription. Your support helps bring new lectures about the mysteries of the universe into these quiet nighttime hours. At the center of Andromeda lies a supermassive black hole whose mass is estimated to be hundreds of millions of solar masses. For comparison, the black hole at the center of the Milky Way has a mass of about 4 million solar masses. This difference suggests that Andromeda's evolution may have progressed at a faster and more dramatic pace than that of our own galaxy. Supermassive black holes grow through mergers with smaller black holes and through the gradual accretion of surrounding matter, silently shaping the destiny of their host galaxies. For this reason, Andromeda's active past is confirmed by the sheer scale of its colossal core. One of the most intriguing features of the central region is the presence of a double nucleus, detected with the help of the Hubble Space Telescope. Visually, it appears as two bright peaks separated by a small distance. Scientists believe this unusual structure may be the result of a merger between two dense star clusters, or a lingering imprint of interaction with the central black hole. Such a phenomenon is rarely observed in other galaxies, making Andromeda a truly unique object of study. Stars located close to the core move at extraordinary speeds. By tracking their paths, astronomers are able to calculate the mass of the central black hole and study the complex dynamics of the system. These observations became some of the most important confirmations of the existence of supermassive black holes at the centers of galaxies. Observations also show that Andromeda's core is not static. It subtly pulses, changes over time, and occasionally shows signs of activity in the form of radiation. Within the central region, astronomers have identified traces of ancient catastrophes, relic clouds of gas that may have remained after powerful stellar outbursts long ago. These clouds serve as quiet witnesses to a time when the core was far more active and may have resembled a quasar, emitting intense energy into surrounding space. Today, the core exists in a calmer phase, yet the echoes of its turbulent past are still preserved within it. Hypotheses about the future of Andromeda's central region are closely tied to the upcoming merger between Andromeda and the Milky Way. When this collision occurs, the supermassive black holes of both galaxies will gradually approach one another and eventually merge. This event will produce an immense burst of gravitational waves, rippling through space-time itself. Such a process may trigger a complete restructuring of the core of the future merged galaxy, becoming one of the most magnificent events in the history of the cosmos. It is important to note that Andromeda's core is a priceless source of information about the physics of dense stellar systems. The density in this region is so extreme that scientists can observe interactions between stars that are almost impossible to detect elsewhere. These insights help refine models of galactic evolution and allow researchers to better predict the future behavior of galaxies. From a scientific perspective, Andromeda's core can be seen as the heart of the entire system. It governs the dynamics, influences the distribution of mass, and sets the overall rhythm of the galaxy's evolution. If we imagine the galaxy as a living organism, the core functions as its control center, where the most essential processes are concentrated. Thus, the central region of Andromeda is not merely an astronomical object, but a unique archive preserving the story of its formation and transformation. Each new observation reveals additional details, gradually assembling a clearer picture of how giant galaxies are born, grow, and change across the universe. One of the primary subjects of research in Andromeda is its spiral arms. They are not only responsible for the galaxy's striking beauty, making it resemble our own Milky Way, but also serve as arenas of active star formation. These immense structures are composed of billions of stars, vast gas clouds, and dark dust lanes, forming intricate and flowing patterns across the galactic disk. Before we explore them more deeply, gently remember to support the channel with a like and a subscription, so that new scientific lectures can continue to appear regularly. The spiral arms of Andromeda are regions of increased matter density. Their shape is maintained by density waves, gravitational waves that travel through the disk of the galaxy. These waves act like cosmic architects, organizing the movement of stars and gas. As a density wave passes through, gas clouds are compressed, triggering the birth of new stars. In this way, the spiral arms can be seen as a conveyor belt, where luminous stars are continuously formed. Particular attention is drawn to the giant molecular clouds located within the arms. They are the primary sources of star formation. Inside these clouds, gravitational collapse occurs, causing gas to condense and form protostars. As a result, new stellar clusters are constantly emerging in Andromeda, confirming that the galaxy remains actively evolving. Some of these stars will one day explode as supernova, enriching the interstellar medium with heavy elements. Interestingly, the structure of Andromeda's spiral arms is asymmetrical. Unlike the perfectly balanced spirals often depicted in illustrations, one of Andromeda's arms appears more massive and brighter than the other. Scientists attribute this imbalance to the influence of satellite galaxies such as M32 and M110. Their gravitational pull disturbs the equilibrium of the system, creating subtle scars within the spiral structure. These distortions can be interpreted as traces of hidden pathways, signs pointing to past collisions and interactions that shaped Andromeda into the galaxy we observe today. Infrared observations have revealed that the spiral arms of Andromeda contain vast amounts of cosmic dust. This dust plays a crucial role in cooling interstellar gas and enabling the formation of new star systems. At the same time, it absorbs visible light, making certain regions invisible in the optical range. This creates the illusion of emptiness, even though entire complexes of stars and gas clouds are hidden within these darkened zones. In this way, Andromeda quietly conceals its most active regions behind soft veils of cosmic dust. Scientists also use Andromeda's spiral arms to test theories about the distribution of dark matter. By measuring the rotation speeds of different regions of the galaxy, astronomers can determine how dark matter is spread throughout space. These measurements confirm that Andromeda's dark matter halo extends far beyond the visible disk and plays a decisive role in holding the entire structure together. Hypotheses about the origin of the spiral arms suggest that their shape has changed over time. According to theoretical models, several billion years ago, Andromeda may have possessed denser and more clearly defined spirals. Over time, interactions with other galaxies and internal rearrangements disrupted their symmetry. What we observe today is the result of these slow cosmic processes, a unique pattern that continues to evolve even now. It is important to emphasize that spiral arms are not static structures. They exist as dynamic zones where matter is constantly moving, colliding, and transforming. If we compare a galaxy to a living city, then the spiral arms are its bustling streets, places where new generations of stars are born. That is why studying them gives us insight into the future of galaxies and the mechanisms by which they sustain their life cycles. Thus, Andromeda's spiral arms are not merely a beautiful feature of its appearance, but a key to understanding fundamental processes occurring throughout the universe. Their asymmetry, active star formation, and interaction with dark matter turn them into a unique laboratory where the laws of the cosmos unfold before us. Of great importance in the study of Andromeda are its star clusters. These structures can be seen as the building blocks of the galaxy, preserving information about its distant past. Star clusters are divided into two main types: globular clusters and open clusters. Andromeda contains thousands of them, and each cluster is an archive in which the history of star formation is carefully recorded. If you enjoy these details and would like to listen to scientific sleep lectures more often, gently support the project with a like and a subscription. Globular clusters are dense formations consisting of hundreds of thousands of stars bound together by gravity. They are among the oldest objects in the galaxy, with ages exceeding 10 billion years. More than 500 such clusters are known in Andromeda, and some of them are truly extraordinary. One notable example is G1, one of the largest globular clusters in the entire local group. Its mass is comparable to that of a dwarf galaxy, and its structure suggests that it may be the remnant core of a galaxy that was once absorbed by Andromeda. Open clusters, in contrast, are younger and contain fewer stars, typically from a few dozen to several thousand. They are located mainly within the spiral arms and serve as clear evidence of ongoing star formation. By studying these clusters, astronomers can determine how quickly new stars are forming in Andromeda and how they are distributed across the galactic disk. The chemical composition of stars within these clusters is of particular interest. It reveals that Andromeda formed in stages. Older globular clusters consist primarily of light elements, such as hydrogen and helium, while younger clusters are enriched with heavier elements: carbon, oxygen, iron. This occurs because each new generation of stars inherits material ejected by supernova in earlier eras. In this way, star clusters allow us to trace an unbroken chain of cosmic construction, spanning billions of years. Star clusters also help researchers study Andromeda's dark halo. Their orbits extend far beyond the visible disk, and by tracking their motion, scientists can infer the distribution of invisible mass. These observations confirm that the dark matter halo stretches for hundreds of thousands of light years and contains the majority of the galaxy's total mass. An intriguing fact is that some clusters in Andromeda possess unusual characteristics. They may exhibit elongated shapes, which is uncommon for globular clusters. Scientists suggest that such objects may have formed as a result of collisions or mergers. In essence, these clusters act as hidden passages into the galaxy's past, pointing toward episodes of intense interaction and transformation. Hypotheses regarding the origin of the largest clusters propose that many of them are not independent structures, but the surviving cores of galaxies that were long ago absorbed. Their centers endured, preserved as dense stellar formations. Thus, by studying Andromeda's star clusters, we are able to reconstruct a detailed picture of the many collisions and mergers that shaped this galaxy billions of years ago. In addition, star clusters provide a rare opportunity to study the dynamics of stellar systems under conditions of extreme density. In their central regions, stars are packed so closely together that the probability of interactions increases many times over. These environments create unique conditions for the formation of exotic objects, such as binary systems of neutron stars or even pairs of black holes. In this sense, star clusters in Andromeda are far more than beautiful points of light visible through a telescope. They are repositories of information about the galaxy's past, keys to understanding the processes of star formation, and powerful tools for exploring dark matter. Through them, scientists uncover the hidden workings of the cosmos and gain insight into how vast systems like Andromeda are built and how they evolve over time. Andromeda itself is not only a massive spiral galaxy, but a complex system surrounded by numerous companions. These smaller galaxies orbit it much like planets orbit a star, slowly reshaping its structure through gravitational influence. The study of Andromeda's satellites allows astronomers to better understand how large galaxies grow and evolve. If you would like to hear more scientific sleep lectures like this, gently support the project with a like and a subscription. The largest companions of Andromeda are the elliptical galaxies, M32 and M110. Both can be observed even with relatively small telescopes and are deeply connected to Andromeda's history. M32 is a compact elliptical galaxy located very close to Andromeda's disk. It is so small that its stars follow extremely tight orbits. Scientists believe that in the distant past, M32 may have been much larger, but Andromeda gradually stripped away its outer layers through gravitational interactions. M110, by contrast, has a more elongated shape and a lower overall density. Its structure shows clear signs of disruption. Stars in its outer regions appear to be stretched into space, as if being gently pulled apart. This serves as evidence that M110 too is slowly being absorbed by its giant neighbor. In this way, we are witnessing the construction of Andromeda through the gradual consumption of smaller systems. Beyond these two bright companions, more than 24 dwarf galaxies are known to be gravitationally bound to Andromeda. Many of them are faint and low-mass objects, difficult to detect. Yet their importance is immense. They serve as the raw material for the growth of the central galaxy. Each merger leaves behind traces, stellar streams, subtle distortions, and an enrichment of the core with new elements. A particularly intriguing discovery emerged from recent analyses of the distribution of Andromeda's satellites. It was found that many of them form a kind of disk, aligned within a specific plane. This observation challenges existing models of galaxy formation, which predicted a far more chaotic arrangement. It is possible that we are encountering a previously hidden pathway of galactic evolution, one that is not yet fully understood. These satellite galaxies are not merely building blocks, they are valuable scientific laboratories. Within them, astronomers can study star formation under conditions of low mass and low density. Some dwarf galaxies have lost nearly all of their gas, leaving behind what resembles a bare stellar core. Others still contain clouds of hydrogen and continue forming new stars. This diversity allows scientists to compare different stages of galactic evolution in a natural and observable way. Hypotheses about the future of these satellites suggest that many of them will gradually disappear under Andromeda's gravitational pull. Over the next several billion years, most will be absorbed. As a result, Andromeda itself will become even more massive, and its structure will continue to change. This process can be seen as a natural mechanism of growth, characteristic of all large galaxies in the universe. Moreover, interactions with satellite galaxies can induce distortions within Andromeda itself. Their gravitational influence is capable of altering stellar trajectories in the disk, creating waves and subtle warps. Some of the asymmetries observed in Andromeda's spiral arms are explained in precisely this way. All of this reminds us that a galaxy is a living, dynamic system, constantly shaped by external forces. Andromeda's satellites are not merely its surroundings, they are part of its destiny. Their existence shows that galaxies are not isolated islands, but elements of an intricate network of cosmic interactions. By studying them, we move closer to understanding how the universe constructs its greatest structures. One of the most important directions in the study of Andromeda is the exploration of its halo. This term refers to the vast region surrounding the galaxy, extending far beyond the limits of the visible disk. And here, the story of Andromeda quietly continues, unfolding in the darkness between the stars. The halo of Andromeda is composed of stars, dark matter, and hot gas. It plays a fundamental role in holding the entire structure together and reflects the long and complex history of the galaxy. If the theme of space and scientific discovery resonates with you, gently support this lecture with a like and a subscription. This helps the project continue to grow. The stellar halo of Andromeda contains very old stars whose ages reach 10 billion years and more. These stars are remnants of ancient star formation processes that took place during the earliest stages of the galaxy's evolution. Within the halo, scientists have also discovered traces of destroyed dwarf satellites that were once absorbed by Andromeda. Their stars have been stretched into long, delicate streams, forming hidden pathways through the galaxy's past, quiet signatures of ancient cosmic encounters. Of particular importance is the dark halo. Its existence cannot be observed directly, yet it reveals itself through the motion of stars. Without dark matter, the gravity of visible objects alone would not be sufficient to hold Andromeda together in its present form. Calculations show that the mass of Andromeda's dark halo exceeds the total mass of all its stars by tens of times. This invisible structure extends for hundreds of thousands of light years, forming a vast framework upon which the entire galaxy rests. The halo of Andromeda also contains hot gas. Using space telescopes, astronomers had discovered that it emits radiation in the X-ray range. This gas acts as a kind of reservoir from which future star formation may occur. Its temperature reaches millions of degrees, and it can stretch across enormous distances. Scientists believe that a significant portion of the galaxy is baryonic matter. Ordinary matter made of protons and neutrons is concentrated within this halo. For a long time, it remained hidden from observation, quietly surrounding the visible galaxy. Studies of the halo have revealed surprising structures. For example, it has been found to be asymmetric. One side is denser and richer in stars than the other. This imbalance may be the result of relatively recent collisions with dwarf galaxies. Such observations help reconstruct the sequence of events that shaped Andromeda over billions of years, like reading faint traces left behind in cosmic dust. Hypotheses about the origin of the halo suggest that it formed through the gradual accumulation of matter. At first, it consisted of stellar remnants and gas expelled by supernova explosions. Later, stars from absorbed satellite galaxies were added. Dark matter, in turn, may have emerged at the earliest stages of the universe itself, providing the foundation for future galactic growth. Particular attention is drawn to the connection between Andromeda's halo and the halo of the Milky Way. Some scientists suggest that their outer regions may already partially overlap. If this is true, then the interaction between our galaxies began long before their eventual merger. This hypothesis reminds us that the destinies of these two giants are deeply intertwined. Thus, the halo of Andromeda is a key to understanding both its past and its future. It preserves traces of ancient stars, destroyed satellites, and long-lasting star formation processes. Dark matter and hot gas make it a fundamental component of the entire system. By studying the halo, we uncover the hidden mechanisms that allow the galaxy to maintain its shape and continue its existence. One of the most important areas of Andromeda research is the study of its kinematics, the motion of stars, gas, and satellite galaxies. It is through these movements that we can understand how the galaxy is structured from within and which forces govern its evolution. The kinematics of Andromeda became one of the decisive arguments in favor of the existence of dark matter. Before we go deeper, gently support this lecture with a like and a subscription to help the scientific project continue. Measurements have shown that Andromeda's rotation speed remains high even at great distances from its center. According to the laws of Newtonian mechanics, this speed should decrease with distance from the core, as it does in planetary systems. However, stars and gas in the outer regions rotate almost as fast as those closer to the center. This became one of the first direct pieces of evidence that the galaxy is surrounded by an invisible mass, dark matter. To study motion within Andromeda, astronomers use spectroscopic methods. By measuring shifts in spectral lines, they can calculate whether objects are moving toward us or away from us. These measurements allow scientists to create detailed maps of the motion of stars and gas. For example, it has been established that gas within the spiral arms moves more coherently than stars, while in certain regions, turbulent flows are observed. This points to complex processes associated with star formation and interactions with neighboring galaxies. Special attention is given to the motion of Andromeda's satellites. Their orbits show that they are bound by the shared gravity of the massive system. However, the distribution of these orbits turned out to be unusual. Many satellites are arranged within a plane that does not align with classical models. This peculiarity has led to hypotheses suggesting that they may have been captured during a single event, such as a collision or merger with a larger galaxy. The kinematics of the central region also holds its own mysteries. And in the quiet motion of stars, the galaxy continues to whisper its secrets, slowly and endlessly, through the darkness of space. Observations of the motion of stars around the galactic core have revealed something intriguing. They suggest that there may be not one, but several massive black holes hidden within the center. This hypothesis helps explain the complex orbital paths and the unusual distribution of stellar velocities observed there. If confirmed, Andromeda would become a rare example of a galaxy in which the process of merging supermassive black holes is actively taking place. Another fascinating fact is that the entire galaxy is moving toward the Milky Way. The radial velocity of Andromeda is approximately 300 kilometers per second in our direction. This means that in about 4 to 5 billion years, an inevitable collision will occur. The kinematics of both galaxies indicate that they are highly likely to merge into a single unified system. Scientists also consider alternative hypotheses that attempt to explain the unusual motion of stars. One of these ideas is related to modified Newtonian dynamics, which proposes changes in the laws of gravity on very large scales. However, most observational data still align more convincingly with the dark matter model. Thus, the kinematics of Andromeda open hidden pathways into the structure of the galaxy itself. The motion of stars, gas, and satellites reflects the influence of both visible matter and an invisible gravitational framework. By studying these movements, we come closer to understanding the fundamental laws that govern the universe. One of the most important aspects of Andromeda research is its formation history. This galaxy did not appear fully formed. Instead, it was assembled piece by piece over billions of years. Traces of its evolution can be found in the structure of its disk, in stellar streams, and in the chemical composition of its stars. All of this allows scientists to reconstruct the events that shaped Andromeda from the moment of its birth. If this kind of scientific perspective resonates with you, gently support the project with a like and a subscription. This helps make more lectures like this possible. Models show that Andromeda began forming more than 10 billion years ago, shortly after the first stars and galaxies appeared in the universe. The earliest proto-galaxies were clouds of gas and dark matter that gradually merged, forming increasingly larger structures. Andromeda grew through the unification of many smaller systems. That is why, even today, remnants of ancient stars and dwarf satellites can be found within its halo. Of particular importance are the stellar streams observed around Andromeda. They are direct evidence of its growth through mergers. Each of these rivers of stars is the lingering trace of a destroyed galaxy that once orbited Andromeda. By studying their distribution and the ages of their stars, astronomers can date events that occurred billions of years ago. A crucial stage in Andromeda's evolution was a period of intense star formation, which calculations suggest occurred around 2 billion years ago. During this time, an unusually large number of stars were formed, increasing the galaxy's brightness and mass. The cause of this burst may have been a collision with another large galaxy, or a powerful inflow of gas from intergalactic space. This era left deep imprints on Andromeda's structure and became a turning point in its history. Chemical analysis of its stars reveals a complex, multi-layered past. Older stars contain very small amounts of heavy elements, while younger ones show much higher concentrations. This points to repeated cycles of star formation and destruction. Each new cycle enriched interstellar space with heavier elements, creating the conditions necessary for the formation of planetary systems. Another important clue lies within the structure of Andromeda's disk. Scientists have discovered wave-like features that may have formed after collisions with other galaxies. These waves appear as distortions and deformations that cannot be explained by internal processes alone. This suggests that Andromeda experienced at least one major merger in the past. Some hypotheses even propose that Andromeda's very shape is the result of transformation. It is possible that it originally had an elliptical form, and that its spiral structure emerged later through gas accretion and dynamic rearrangements. This idea does not yet have definitive proof, but it is actively discussed within the scientific community. Thus, Andromeda is not a static system. It is the result of continuous construction. Every merger, every cycle of star formation, and every influx of matter has shaped its present appearance. By studying these processes, we not only uncover the past of our neighboring galaxy, but also gain a deeper understanding of the evolution of the entire universe, slowly, quietly, and written across billions of years in starlight. One of the most important tools for studying the Andromeda galaxy has become observation across different regions of the electromagnetic spectrum. By doing this, scientists are able to see processes that remain hidden from optical light and gain a far more complete picture of how the galaxy truly works. If science and space feel close to you, gently support this lecture with a like and a subscription. This helps the project grow and allows new sleep-friendly materials to be created. In the optical range, Andromeda appears as a bright spiral galaxy with clearly defined arms and a luminous central core. This is the familiar image most people recognize from telescope photographs and amateur astrophotography. However, optical observations reveal only part of the story, because dust and gas block a significant portion of the visible light. In the infrared range, entirely new details emerge. Dust that hides stars in visible light becomes almost transparent at infrared wavelengths. This allows astronomers to observe regions of active star formation and uncover hidden stellar clusters. Observations made with the Spitzer Space Telescope have shown that Andromeda's spiral arms are rich in warm dust and molecular gas, the very material from which new stars are born. Radio wavelengths also play a crucial role. They make it possible to study clouds of hydrogen that are invisible in optical light. In Andromeda, vast amounts of neutral hydrogen have been detected, spread throughout the disk and extending into the halo. Radio observations also help trace the motion of gas and reconstruct detailed maps of how matter flows within the galaxy. X-ray observations reveal a picture of high-energy processes. Using space observatories, scientists have detected numerous X-ray sources within Andromeda. These include binary systems containing black holes and neutron stars, as well as remnants of supernova explosions. Such objects help us understand how stars end their life cycles and how their final moments influence the surrounding space. Ultraviolet observations are especially fascinating. They allow astronomers to detect young, hot stars that emit strongly in this range. Thanks to the Galaxy telescope, a large number of young star clusters have been identified in Andromeda's spiral arms, confirming that star formation there remains active and ongoing. When all these data are combined, a multi-layered image emerges. In optical light, infrared, radio waves, ultraviolet, and X-rays, Andromeda can appear almost like several different objects. Yet together, they reveal a single living system where dozens of processes unfold simultaneously. This can be compared to medical tomography. Each method provides a different slice, but only together do they create a complete picture. Future observations promise even deeper insights. For example, the James Webb Space Telescope has already begun studying star formation in Andromeda with unprecedented detail. Its extraordinary sensitivity allows it to peer into the densest dust clouds where stars are just beginning to form. In the coming years, these observations may significantly change our understanding of the galaxy's evolution and internal dynamics. Thus, multi-wavelength observations reveal hidden pathways within Andromeda's structure. Each new study in each part of the spectrum adds another piece to the greater picture, allowing us to see not only the galaxy's appearance, but also its inner workings. For science, this is an opportunity not just to explore a neighboring galaxy, but to better understand the mechanisms that govern the entire universe. Andromeda has long been a subject not only of astronomical research, but also of cosmological models that help define our place in the larger structure of the cosmos. It is part of what is known as the local group of galaxies, where it plays a dominant role alongside the Milky Way. Studying this group helps answer questions about how galactic communities form and how they evolve over time. Support this lecture with a like and a subscription so you can continue listening to gentle scientific stories before sleep. The local group includes more than 50 galaxies, most of them small dwarf systems. Its main members are Andromeda, the Milky Way, and the Triangulum Galaxy. These three giants define the gravitational structure of the entire group. Andromeda is the largest and likely the most massive among them. That is why its future is directly tied to the fate of this entire cosmic family. One of the key questions concerns Andromeda's interaction with the Milky Way. Even today, their dark matter halos may already be partially overlapping. This suggests that the exchange of matter and gravitational influence began long before their eventual collision. In 4 to 5 billion years, a complete merger will occur, reshaping the local group entirely. The Triangulum Galaxy also plays an important role. Although it is smaller than Andromeda and the Milky Way, its mass and position make it a significant participant in these interactions, quietly orbiting, influencing, and responding to the slow cosmic dance unfolding over billions of years. And as this vast choreography continues, Andromeda remains a calm, distant storyteller, revealing its secrets slowly, softly, and patiently, written across the quiet fabric of space and time. Some models predict that the Triangulum galaxy may be the first to engage in a close interaction with Andromeda, leading to a restructuring of its spiral arms and disk. This would serve as a kind of prelude to the much larger event, the eventual merger with the Milky Way. Interestingly, the local group is not isolated. It is part of the larger Virgo supercluster, which contains thousands of galaxies. In this vast context, Andromeda is just one of many giant systems, though it holds special significance for us because of its proximity. By studying it, we can better understand the patterns that govern the universe as a whole. Cosmological models show that groups like ours are temporary formations. Over time, gravity draws galaxies together into larger structures, while the accelerated expansion of the universe gradually separates distant clusters. In the distant future, tens of billions of years from now, the local group may evolve into an isolated massive galaxy, with all other systems receding ever farther due to cosmic expansion. A particularly intriguing question concerns the role of dark energy. It is this mysterious force that drives the accelerating expansion of the universe. For Andromeda, this means its fate is shaped not only by local interactions, but also by the global laws of the cosmos. Even if it merges with the Milky Way, the resulting combined system will continue to drift away from other galaxies, carried along by the universe's expansion. Thus, Andromeda is not only our nearest giant neighbor, but also part of a complex hierarchy of cosmic structures. Its interactions with other members of the local group and its future merger with the Milky Way illustrate the principles by which the universe evolves. By studying Andromeda, we glimpse the hidden mechanisms that shape the fates of individual galaxies and entire clusters. One of the most important areas of research in Andromeda is the study of its supernova. These cosmic explosions are not only spectacular events, but also keys to understanding galactic evolution. Supernova in Andromeda have been observed for centuries, and their remnants continue to be studied with modern telescopes. There are two main scenarios for the formation of supernova. The first involves massive stars that end their lives in core collapse. The second involves white dwarfs in binary systems that accumulate material until they reach a critical mass. In both cases, the outcome is an enormous explosion, releasing immense energy and ejecting matter into space. Andromeda is famous for hosting one of the first supernovae observed beyond the Milky Way. In 1885, German astronomer Ernst Hartwig discovered a bright explosion, later named S. Andromedae. This event was a landmark, proving that the same stellar processes occur in other galaxies. The supernova was so bright, it could be seen with the naked eye. Today, astronomers study supernova remnants as expanding shells of gas. These shells emit light in optical, X-ray, and radio wavelengths, carrying information about the composition of the ejected matter. Thanks to supernova, the universe becomes enriched with heavy elements, the building blocks of planets and life itself. Supernova are closely linked to star formation. Andromeda continues to birth new stars, including many massive ones that will eventually explode. This creates a cycle: Earth, life, explosion, enrichment of the interstellar medium, and formation of the next generation of stars. It is, in a sense, a cosmic technology that sustains continuous evolution. Interestingly, some regions in Andromeda show unusually high densities of supernova remnants. This indicates past episodes of intense star formation, possibly triggered by galaxy mergers and collisions of gas clouds. Future supernova are expected, some bright enough to be visible from Earth. Observing such events in real time will provide unique scientific data that cannot be obtained in any other way. Thus, supernova in Andromeda are not merely a spectacle. They are fundamental processes that shape the galaxy's chemical makeup, influence gas dynamics, and set the stage for new generations of stars. By studying them, we gain access to the hidden mechanisms guiding the evolution of the universe. One of the greatest mysteries of Andromeda is the distribution of dark matter. This invisible component makes up the majority of its mass and determines the gravitational structure of the entire system. Although dark matter neither emits nor absorbs light, its presence is revealed through the motion of stars and gas. If you feel drawn to the wonders of space, supporting this lecture with a like and subscription helps the project continue and allows new research to emerge. The strongest evidence for dark matter in Andromeda comes from its rotation curve. Measurements show that stars maintain nearly constant speeds, even at large distances from the center. According to Newtonian physics, the speed should decrease with distance if the galaxy's mass were contained only in visible objects. But that does not happen. The only explanation is the presence of an extensive halo of dark matter holding the system together. Calculations suggest that the mass of dark matter in Andromeda is tens of times greater than the mass of all its stars and gas. This halo extends for hundreds of thousands of light years, forming an invisible framework. It not only stabilizes the stars, but also influences the dynamics of satellite galaxies. Their orbits follow the distribution of dark matter, as confirmed by observations. A fascinating discovery is the asymmetry in the dark matter halo. One side is denser and richer in stars than the other, likely a trace of past mergers and interactions, a hidden path in the galaxy's long and dramatic history. The halo of Andromeda is not perfectly spherical. It is slightly elongated. This elongation may result from interactions with neighboring galaxies or the aftermath of past mergers. This asymmetry provides hidden paths to understanding Andromeda's structure, pointing to its dynamic past. Astronomers also use Andromeda as a testing ground for various models of dark matter. There are hypotheses that it may consist of weakly interacting particles, massive compact objects, or even represent a manifestation of modified gravity. Each of these ideas is tested by modeling the motion of stars in Andromeda and comparing the results with observations. An important fact is that dark matter determines the fate of the impending collision between Andromeda and the Milky Way. The mass of the halos of both galaxies creates a mutual attraction that will inevitably bring them together. Without this invisible component, they could have drifted apart, never colliding. In this way, dark matter governs the future of both systems. Modern telescopes, such as Hubble and James Webb, along with radio observation projects, help refine the distribution of dark matter. Analysis of stellar streams and satellite orbits allows astronomers to create increasingly detailed maps. These maps reveal the complex structure of the halo, which had remained hidden until now. Hypotheses about the nature of dark matter remain some of the greatest questions in modern physics. Andromeda serves as a living laboratory in this context. Each new measurement of its dynamics brings us closer to an answer. Perhaps by observing this neighboring galaxy, we may one day understand the true nature of the invisible mass in the universe. Thus, dark matter in Andromeda is not just an invisible shell. It is fundamental to the galaxy's existence. It determines the motion of stars, the fate of satellites, and the future collision with the Milky Way. By studying its distribution, we approach one of the greatest mysteries of modern science. Andromeda is fascinating not only for its structure, but also for the chemical composition of its stars and gas. This aspect allows astronomers to understand how its matter evolved and what processes shaped its appearance. Analysis of elements in stars and gas clouds provides insight into how the galaxy built itself over billions of years. The chemical composition of stars in Andromeda shows that the galaxy underwent multiple stages of star formation. The oldest stars in its halo contain mostly hydrogen and helium, with almost no heavy elements. This indicates that they formed shortly after the birth of the universe, before heavy elements had accumulated. In contrast, younger stars are enriched with metals. In astronomy, this term refers to all elements heavier than helium. This enrichment is the result of supernova, which over billions of years released carbon, oxygen, iron, and other elements into space. Especially important is the analysis of stellar metallicity, the fraction of heavy elements in a star. In Andromeda, an interesting pattern emerges. Stars in the central regions have high metallicity, while those in the outskirts have low metallicity. This confirms that star formation in the core was more active, while the outer regions developed more slowly. Gas clouds in Andromeda also show diversity in composition. Spectral observations reveal large amounts of hydrogen, along with traces of oxygen, nitrogen, and sulfur. These data allow astronomers to assess the galaxy's chemical evolution and compare it with the Milky Way. Thus, the search for exoplanets in Andromeda is still in its early stages, yet the probability of their existence is extremely high. This perspective makes our neighboring galaxy not only an object for studying structure and dynamics, but also a potential source of answers to humanity's greatest question. Are we alone in the universe? Andromeda holds countless stellar relics, ancient objects that allow us to look into the galaxy's past. These stars and systems formed in its earliest stages and have survived to this day. Studying them offers insight into how the first structures in the universe were born. Among the oldest objects in Andromeda are halo stars. Their ages exceed 10 billion years, and their chemical composition shows extremely low amounts of heavy elements. This means they formed before the universe had been enriched by the products of supernova explosions. These stars are direct witnesses of the earliest epochs of cosmic history. Particular interest is drawn to so-called ultra-compact dwarf systems. Some of them in Andromeda have been discovered relatively recently. By their characteristics, they resemble the cores of dwarf galaxies stripped of their outer layers. They are likely remnants of systems absorbed by Andromeda billions of years ago, and can be considered hidden pathways to its past. Stars with anomalous element abundances in Andromeda also hold keys to understanding its construction. For example, some objects show elevated oxygen or iron content, indicating localized bursts of star formation and supernova explosions in specific regions. These data help reconstruct the picture of chemical evolution. An intriguing area of research is the search for relic stars in Andromeda's globular clusters. They may preserve objects formed shortly after the Big Bang. Their spectra contain information about the composition of the primordial matter that existed in the early universe. In this way, studying clusters in Andromeda helps us understand how the first generations of stars formed. Some hypotheses suggest that Andromeda absorbed several relatively large galaxies in the past. Remnants of their stars can be found among relic objects. This explains the presence of stars with varying characteristics that do not fit standard models of its evolution. Essentially, Andromeda is a mosaic of many ancient systems. With modern telescopes, astronomers can even identify individual stars within Andromeda, offering a truly unique opportunity for study. This allows astronomers to study their age, chemical composition, and motion. Such data provides direct evidence of how the galaxy grew over billions of years. Thus, the relic stars and systems in Andromeda are its ancient memory. They preserve information about the earliest epochs, about mergers, and structural changes. By studying them, we can understand how the universe built its first large-scale structures and how they evolved into the galaxies we see today. Despite its enormous distance, Andromeda has become a subject of measurements with precision comparable to studying stars within our own galaxy. Astronomical methods allow determining its distance, velocity, and even structural features. These studies not only reveal the secrets of a neighboring galaxy, but also help calibrate the scale of the universe itself. If you enjoy learning such facts, support the project with a like and subscription. This motivates the creation of new bedtime science lectures. Determining the distance to Andromeda became one of the most important discoveries in the history of astronomy. In the early 20th century, Edwin Hubble used Cepheid special variable stars, whose brightness correlates with their pulsation period. By observing Cepheids in Andromeda, he proved that this nebula lies beyond the Milky Way and is a separate galaxy. This discovery was a turning point in science. The universe turned out to be much larger than previously thought. Today, the distance to Andromeda is estimated at about 2.5 million light-years. To refine this value, astronomers use not only Cepheids, but also other methods. Analysis of red giant branch stars, type Ia supernova, and comparisons of stellar populations with models. This precision allows Andromeda to serve as a benchmark for measuring distances to more distant objects. Measuring Andromeda's motion also became possible thanks to the Doppler effect. Spectroscopy showed that it is approaching us at a speed of about 300 kilometers per second. This means that in the future, it will collide with the Milky Way. These data formed the basis for calculations of the dynamics of the entire local group. Interestingly, in addition to radial velocity, scientists have been able to detect Andromeda's transverse motion. This required decades of observations with the Hubble Space Telescope. These measurements confirm that its trajectory indeed leads to a merger, not a flyby. This result firmly established our understanding of the future of our galaxy. Special attention is given to measuring stellar streams and Andromeda's satellites. Their motion allows for refining the distribution of mass and dark matter. These data are used to build computer models that reproduce its past and predict the future. Hypotheses regarding measurement accuracy also include discussion of errors. For example, different methods sometimes produce slightly different results, and scientists continue to reconcile them. However, these discrepancies are minor and do not change the overall picture. Thus, measuring Andromeda's distance and velocity has turned it into a key object in cosmology. It has become a kind of cosmic ruler, allowing us to measure the universe. By studying it with maximum precision, we obtain fundamental data that help us understand the scale and dynamics of space. One of the most impressive directions in studying Andromeda is computer modeling of its future. With modern supercomputers, scientists can simulate its evolution and predict how the galaxy's structure will change over billions of years. These simulations allow us to see the fate not only of Andromeda, but of the entire local group. To keep new lectures coming, support the project with a like and subscription. This helps develop scientific materials for bedtime learning. The foundation for modeling includes data on Andromeda's mass, the distribution of stars, gas, and dark matter. Using these, scientists calculate gravitational interactions between billions of objects. Of course, it is impossible to track every individual star, so simplified models are used that follow general laws of dynamics. Simulation results show that in about 4 billion years, Andromeda will begin colliding with the Milky Way. This event will unfold over time. The first signs of interaction will appear as disk deformations and the emergence of stellar streams. Gradually, the galaxies will start merging, and over several billion years, form a single massive system. Interestingly, in such a collision, the likelihood of actual star-to-star impacts is extremely low. The distances between stars are so vast that they will mostly pass by one another. The main changes will occur in the gravitational structures. Stellar orbits will shift. Some stars may be ejected into intergalactic space, and the galactic cores will merge into a single supermassive black hole. Models predict that the result will be a new elliptical or lenticular galaxy, provisionally called Andromeda. It will become the largest object in the local group, containing trillions of stars. Its structure will differ from the familiar spiral form. The spiral arms will disappear, and stars will be distributed more evenly. An interesting consequence of the collision will be a burst of star formation. When gas clouds from both galaxies collide, they will compress, leading to the formation of millions of new stars. This event will transform the appearance of the future system, making it brighter for millions of years. Hypotheses about Andromeda's future also consider the influence of the Triangulum galaxy. In some models, it interacts with Andromeda before the Milky Way, complicating the dynamics. In other scenarios, Triangulum becomes involved only after the merger of the two giants, enhancing the restructuring processes. It is important to note that these models depend on the accuracy of initial data. The more information astronomers collect about the orbits and masses of the galaxies, the more precise the predictions become. Already today, simulations allow scientists not only to predict the future, but also to reconstruct past collisions that shaped Andromeda. Thus, computer models give us a glimpse billions of years ahead. They show that Andromeda is not a static object, but a dynamic system whose fate is closely tied to our galaxy. Studying its future gives us insight into how the universe evolves and what processes determine its development. Observing Andromeda, astronomers continue discovering new categories of stellar objects, which help understand how the galaxy evolves. Among them, variable stars hold a special place. These stars change in brightness over time, and studying them has been key to solving many cosmic mysteries. Variable stars are classified into several types. The most famous are Cepheids. Their brightness changes with a clear periodicity linked to internal pulsations. The longer the period, the higher the star's luminosity. This relationship allowed Cepheids to be used as standard candles for measuring distances. It was thanks to them that Edwin Hubble proved Andromeda lies beyond the Milky Way. Another important type of variable stars are novae explosions on the surfaces of white dwarfs, temporarily increasing their brightness. Many such events have been recorded in Andromeda. Each one serves as a laboratory for studying stellar interactions in binary systems and thermonuclear processes. Long-period variables are also observed in Andromeda red giants, whose brightness changes over hundreds of days. These stars are in the final stages of life, expelling enormous amounts of material into space. This material becomes part of the interstellar medium, the building blocks for new generations of stars. Variable stars are especially important for studying Andromeda's structure. Their distribution allows astronomers to construct three-dimensional maps of the galaxy and refine its shape. Thanks to them, it has become clear that Andromeda has a complex, multi-layered structure, including a disk, halo, and central bulge. Interestingly, some variable stars in Andromeda behave unusually. Their periods and amplitudes do not match standard models. This indicates the diversity of stellar populations and shows that Andromeda formed from many different sources. Such stars can be seen as hidden keys to understanding its complex past. Future studies of variable stars will benefit from telescopes like James Webb and new observatories. They will allow scientists to detect even the tiniest changes in brightness and obtain data about stellar atmospheres. This will help refine models of stellar evolution and Andromeda's formation history. Thus, variable stars in Andromeda are not only unique objects themselves, but also tools for studying the entire galaxy. Observing them allows measuring distances, reconstructing structure, and uncovering the mysteries of stellar evolution. Thanks to these stars, Andromeda has become a crucial laboratory for testing astronomical theories. Special attention in Andromeda is also given to binary stars and compact objects. These systems provide a glimpse into extreme conditions where the fundamental laws of physics are revealed. Studying them gives scientists data about black holes, neutron stars, and white dwarfs. In Andromeda, many close binary systems have been discovered, where stars are so close that their gravity and mass exchange play a key role. In such pairs, one star may pull material from its companion, forming accretion disks and emitting energy in X-rays. This is why Andromeda is a source of numerous X-ray bursts. Some of these systems contain neutron stars, the ultra-dense remnants of supernova explosions. When a neutron star accretes material from its companion, it emits X-rays, becoming a bright source for space observatories. Observing them helps refine models of matter behavior under extreme densities. Another class includes stellar mass black holes. Several candidates have been identified in Andromeda. Their presence is detected through accretion disks and powerful X-ray bursts. Studying these objects is important for understanding the evolution of massive stars and black hole formation. White dwarfs in binary systems also play a vital role. When they accumulate material from a companion, thermonuclear explosions can occur on their surfaces, appearing as novas. Many such flashes have been recorded in Andromeda. Each such event serves as a mini laboratory, allowing scientists to test theories about thermonuclear reactions and the evolution of stars. Interestingly, the central region of Andromeda shows a dense cluster of X-ray sources. This indicates a high concentration of compact objects and binary systems near the core. They likely formed through dynamic interactions and numerous stellar collisions. Future studies of binary systems in Andromeda are closely linked to the development of gravitational wave astronomy. Mergers of neutron stars and black holes in this galaxy can produce gravitational waves detectable here on Earth. This allows scientists to gather information about processes occurring in a neighboring galaxy, even without optical observations. Thus, binary systems and compact objects in Andromeda are among the most important elements of its structure. They demonstrate extreme states of matter, enrich the galaxy with heavy elements, and serve as sources of observable radiation. Studying them helps us understand both stellar evolution and the fundamental laws of physics. Andromeda serves as a unique laboratory for studying its stellar population and the distribution of star ages. Unlike more distant galaxies, where only the combined light is visible, here we can resolve individual stars and study their characteristics. This allows for a detailed picture of the galaxy's evolution. The stellar population of Andromeda is divided into several components. The central region contains old metal-rich stars, indicating intense star formation in the past. The galactic disk, in contrast, hosts younger generations, including hot blue giants and active regions of new star formation. The halo primarily consists of old red giants with low metallicity, remnants from the early universe. A particularly important tool is the map of age distribution. It shows that Andromeda experienced bursts of star formation at different epochs. For example, about 2 billion years ago, a powerful spike occurred, likely triggered by the merger with another galaxy. Traces of this event are visible in the form of young clusters and anomalies in the disk's structure. Comparison with the Milky Way reveals interesting differences. In our galaxy, star formation has been more gradual, whereas Andromeda has undergone sharp fluctuations. This makes it an example of more dynamic development, linked to numerous collisions and accretions. Interestingly, Andromeda contains stars as old as the universe itself. Studying them is especially valuable, as they carry information about the earliest stages of element formation. These objects help refine cosmological models and test theories about the early evolution of matter. Hypotheses about Andromeda's future stellar population are closely tied to the upcoming merger with the Milky Way. When the two galaxies unite, their stars will mix, and the age distribution will become more complex. Meanwhile, the burst of star formation will create a new generation of young stars, reshaping the appearance of the future system. Thus, Andromeda's stellar population reflects both its history and destiny. It preserves traces of ancient epochs, testifying to catastrophic events and cycles of star formation. By studying age distributions, we uncover the hidden paths through which the galaxy developed over billions of years. Andromeda is interesting not only as an individual galaxy, but also as a key object for studying the interstellar medium. The gas and dust filling its disk and surroundings play a central role in star and planetary system formation. These components are not mere background, they actively shape the galaxy's dynamics. The interstellar medium of Andromeda consists of three main components: cold gas, warm gas, and dust. Cold gas, primarily neutral hydrogen, forms extensive clouds where new stars are born. Warm, ionized gas is less evenly distributed and participates. in the circulation of matter. Dust acts as a catalyst, helping clouds cool and facilitating the formation of molecules. Observations in the radio spectrum reveal that Andromeda contains enormous hydrogen clouds, stretching hundreds of thousands of light years. These clouds form a kind of reservoir for future star formation. In certain regions, gas density is higher, and active areas of star formation are observed. Dust in Andromeda is visible in the infrared spectrum, highlighting structures otherwise hidden in optical light. The dust in Andromeda forms lanes that cross the galactic disk, partially obscuring the light of the stars. These structures are particularly noticeable in the spiral arms, where star formation is most active. Infrared observations by the Spitzer telescope reveal that the dust is distributed unevenly, creating natural corridors through which gas flows. Special attention is given to the circulation of matter. Supernova explosions release heavy elements into the interstellar medium, where they mix with gas and dust. These elements eventually become part of new stars and planets. Thus, the interstellar medium is a continuous cycle of birth and destruction, a kind of natural technology. The interaction of Andromeda's interstellar medium with its satellite galaxies is also of interest. When dwarf galaxies pass through its disk, they can either contribute gas or lose some of their own. These processes influence the balance of star formation and leave traces in the disk's structure. It is important to note that Andromeda also exhibits gas flows extending beyond its disk. These streams likely formed from past collisions and may serve as channels for matter exchange with the intergalactic medium. These hidden pathways show that the galaxy is connected to the surrounding cosmos more closely than it seems. Thus, Andromeda's interstellar medium is a dynamic system where stars are born, elements circulate, and processes take place that determine the galaxy's future. Studying its structure and properties helps us understand how conditions for life form in the universe. One of the most fascinating topics in the study of Andromeda is its magnetic field. Although galactic magnetic fields remain relatively poorly studied, they play a crucial role in gas dynamics, star formation, and the propagation of cosmic rays. Andromeda is a unique object in this regard, because its proximity allows such processes to be studied with high precision. Observations show that Andromeda's magnetic field has an ordered structure stretching along the spiral arms. It resembles a vast grid that envelops the galactic disk. The average field strength is estimated at a few microgauss, comparable to the Milky Way's magnetic field. Although weak on cosmic scales, it significantly influences the movement of charged particles. The magnetic field is detected through the polarization of radio waves emitted by cosmic sources. Analysis shows that field lines in Andromeda are more ordered than in some other spiral galaxies, suggesting a stable dynamic environment, and that spiral arm formation is closely linked to magnetic effects. The magnetic field also plays a key role in regulating interstellar gas. It prevents clouds from collapsing too quickly, slowing down star formation. At the same time, magnetic lines guide gas motion, creating natural channels. Thus, the field has a dual function. It restrains and organizes. Interestingly, the magnetic field also helps trap cosmic rays, streams of high-energy particles that move along field lines, interacting with gas and altering its properties. This adds another hidden layer to understanding Andromeda's dynamics. The origin of the magnetic field is hypothesized to involve a dynamo mechanism. According to this theory, the galaxy's rotation and turbulent gas motions can sustain and amplify the field over billions of years. For Andromeda, this model is supported by observations. Its field is stable and envelops the entire galaxy. Future studies with next-generation radio telescopes, such as the SKA and CRIERS, will allow even more detailed exploration of Andromeda's magnetic field. This will provide insights into how it interacts with spiral arms, gas clouds, and stellar streams. Thus, Andromeda's magnetic field is invisible yet fundamental. It influences gas, stars, and cosmic rays, helping shape the galaxy's overall appearance. Studying it opens a new level of understanding about cosmic processes and brings us closer to unraveling the laws of the universe. Andromeda is also fascinating because it hosts powerful stellar explosions and unique phenomena that help us understand the nature of stellar evolution. These events include novae, supernovae, micronovae, and rare explosions occurring in binary systems. They play a key role in shaping the interstellar medium and serve as markers of the galaxy's activity. One of the most frequently observed phenomena in Andromeda is novae. They occur when a white dwarf in a binary system accumulates matter from its companion star. Once the critical mass is reached, a thermonuclear explosion occurs on its surface, causing the star's brightness to rise sharply. In Andromeda, these events are observed regularly, making it one of the most active galaxies in terms of novae. This is due to its enormous number of stars and the high population of binary systems. In addition to novae, Andromeda also hosts micronovae. These events are fainter, but they are also linked to thermonuclear processes on the surfaces of white dwarfs. Their discovery became possible only thanks to modern telescopes capable of detecting small changes in brightness. Such observations help scientists understand how white dwarfs accumulate and release matter. Supernova in Andromeda, though rarer, are extremely important events. Each explosion releases immense amounts of energy and enriches the interstellar medium with heavy elements. These events create the conditions necessary for planets to form, and ultimately, for life itself. Remnants of Andromeda's supernova are studied across different wavelengths, allowing researchers to reconstruct their history. Interestingly, Andromeda also hosts unusual explosions that do not fit standard categories. Some are so-called superluminous supernova, where the brightness exceeds all known models. The causes of these events remain mysterious, and their study continues. They may be connected to rare types of stars or interactions within massive binary systems. Observing such events gives scientists a way to refine physical laws under extreme conditions. Explosions allow the study of nuclear fusion processes, the dynamics of shock waves, and the interaction of matter with magnetic fields. Andromeda serves as a unique laboratory in this regard because its proximity allows such observations with high detail. Future research hypotheses include using next-generation telescopes capable of detecting even the faintest flashes. This will enable a complete map of Andromeda's stellar activity and help determine how its processes differ from those in the Milky Way. Thus, stellar explosions and rare phenomena in Andromeda are not just a spectacle, but a key to understanding galactic evolution. They show how stars live and die, shaping the environment for new generations of stars. By studying them, we reveal the hidden mechanisms that govern the development of the universe. Andromeda is also a significant source of X-ray emission. Observations in this range allow scientists to study processes that are invisible in optical light and reveal the nature of compact objects. X-ray astronomy in Andromeda has uncovered hundreds of sources, many of which are linked to black holes, neutron stars, and tight binary systems. The first X-ray sources in Andromeda were discovered in the mid-20th century using satellite observatories. Today, telescopes like Chandra and XM and Newton provide detailed maps of its X-ray emission. They show that the galaxy hosts several hundred bright sources, located both in the disk and the central region. Most of these sources are associated with close binary systems, where a compact object, either a neutron star or a black hole, accretes matter from its companion. The process releases enormous energy, which is emitted as X-rays. Such systems allow scientists to study the behavior of matter under extreme conditions and refine models of gravity. Special attention is given to Andromeda's central region. Here, the density of X-ray sources is particularly high. This is likely due to the high concentration of stars, which facilitates the formation of binary systems and their evolution into compact objects. The central core of Andromeda, in X-ray light, appears as a cluster of many active points, creating a complex background. In addition to compact objects, X-ray observations have revealed remnants of supernova. Explosions of massive stars leave expanding clouds of gas, which glow in X-rays due to their high temperatures. These objects help us study the propagation of shock waves and the interaction of gas with magnetic fields. Interestingly, some X-ray sources in Andromeda remain unexplained. They show variable flashes, but their nature is still unclear. Perhaps they are new types of objects or systems that do not yet fit existing models. These mysteries make Andromeda even more valuable for future research. Future X-ray astronomy is linked to the development of new observatories. Planned missions will be able to detect faint sources with greater precision and create three-dimensional maps of X-ray emission. This will allow not only the study of Andromeda, but also comparisons with other galaxies, refining universal laws. Thus, Andromeda's X-ray emission is a powerful tool for understanding its structure. It reveals hidden processes in the core, binary systems, and supernova remnants. By studying these sources, scientists move closer to uncovering the deepest secrets of galactic evolution. Andromeda is also a source of optical illusions and phenomena related to observing it from Earth. For many amateur astronomers, it was the first object that revealed the vast scale of the universe. On a clear night, far from city lights, it can be seen with the naked eye as a faint patch of light. Before we go further, don't forget to support the lecture with a like and subscription, which helps release new materials for sleep. Andromeda's optical visibility is determined by its brightness and size. Its angular diameter in the sky is about 3 degrees, 6 times the size of the Moon. However, its surface is faint, so most details can only be seen through a telescope. To the unaided eye, it appears as a faint cloud, barely visible against the starry sky. Historically, many cultures noted this glow. By the 10th century, Arab astronomers described a hazy patch in the constellation Andromeda. In Europe, it became known in the 15th century, thanks to Galileo's telescope. But only in the 20th century was it understood that this is a separate galaxy, not a cloud within the Milky Way. Observing Andromeda depends on conditions. In cities, where light pollution is strong, it is impossible to see. But in dark sky locations, it becomes visible even to the naked eye. Amateur astronomers use binoculars and small telescopes to view its oval shape and bright core. Professional observations are conducted with giant telescopes and space observatories, allowing the study of individual stars and star clusters. Optical illusions occur because Andromeda appears smaller and dimmer than it really is. Long exposure photographs reveal its true scale, stretching across a huge area of the sky, though the human eye perceives only part of the light. This gives the impression that the galaxy hides its true appearance. Another fascinating phenomenon is the sense of depth. When observing Andromeda, it seems closer than it actually is. This is because our brain interprets it as a cloud in the atmosphere, rather than an object millions of light years away. Future observation hypotheses include the development of amateur astronomy technologies. Already today, compact digital telescopes can capture detailed images of Andromeda, even from suburban areas. In the coming decades, these devices will become more accessible, allowing millions of people to observe our neighboring galaxy, as previously only professionals could. Thus, the optical perception of Andromeda is not only a scientific fact, but also a cultural experience. It has become a symbol of the cosmos, accessible to anyone willing to look up at the sky. By studying it, we not only uncover the secrets of the universe, but also feel our own connection to the infinite expanse. Andromeda has become a cornerstone of astronomical history because its observations marked the beginning of a new era in understanding the universe. Discoveries related to this galaxy have forever changed humanity's view of the cosmos. If you enjoy scientific facts like these, supporting the project with a like and a subscription helps release even more lectures for sleep. Until the beginning of the 20th century, most scientists believed that the Milky Way was the entire universe. Objects like Andromeda were called spiral nebulae, thought to be clouds within our galaxy. But in the 1920s, a revolution happened. Astronomer Edwin Hubble, using the 100-inch telescope on Mount Wilson, studied Cepheid variables in Andromeda. These variable stars allowed him to measure distances, and it turned out they were millions of light years away. This meant that Andromeda was a separate galaxy. This discovery shattered the old worldview and showed that our galaxy was just one among many. From that moment, the universe appeared on a new scale. Andromeda became a symbol of the transition from a limited perspective to an understanding of the infinite cosmos. The history of Andromeda's discovery is also connected to the so-called Great Debate of 1920. At that time, two camps of scientists argued over whether spiral nebulae were part of the Milky Way or separate island universes. Hubble's data settled the debate, and the term island universe became attached to galaxies. Besides Hubble, other astronomers played important roles. Walter Baade studied Andromeda's stellar populations and identified two types of stars: young blue stars and old red stars. This distinction became the foundation for classifying stellar populations. His work also refined the distance to Andromeda and helped us understand its structure better. Andromeda became a testing ground for many theories. It was here that new stars were first observed, supernova explosions, and X-ray sources. Each discovery added layers to our understanding of the galaxy's structure and showed that processes in other galaxies are similar to those in the Milky Way. Future hypotheses for Andromeda as a scientific object involve new observatories. The James Webb Space Telescope has already begun studying its star-forming regions, and next-generation radio telescopes will capture minute details of gas motion. Perhaps in the coming decades, we will obtain such precise models of Andromeda that we can predict its evolution with high confidence. Thus, Andromeda holds a special place in the history of astronomy. It became a key to understanding that the universe is infinitely larger than our galaxy. Studying this system turned it into a symbol of scientific breakthrough, a reminder that every star in every galaxy opens new horizons of knowledge. Andromeda is also fascinating as a laboratory for cosmic rays and high-energy processes. These phenomena are invisible to the human eye, yet they play a crucial role in the galaxy's dynamics and the interaction of its components. Cosmic rays are streams of charged particles moving at near-light speeds, influencing gas, magnetic fields, and star formation processes. Supporting the project with a like and subscription helps deliver more scientific lectures about the universe. Cosmic rays in Andromeda are detected through their interactions with interstellar gas and magnetic fields. When high-energy particles collide with gas atoms, they produce gamma rays, which can be recorded by space observatories. These data allowed scientists to map the distribution of cosmic rays in Andromeda's disk and halo. Interestingly, the gamma ray level in Andromeda is lower than expected. With such a large number of stars and a high rate of star formation, the cosmic ray flux was expected to be more intense. One possible explanation is that Andromeda's magnetic field is organized differently than in the Milky Way, allowing cosmic rays to leave the galaxy more quickly. Other hypotheses suggest that supernova explosions in Andromeda occur less regularly or are less powerful than in our galaxy. This could explain the lower generation of cosmic rays. However, there is still the possibility that we are encountering a new yet unknown mechanism that governs their propagation. High-energy processes in Andromeda also include activity in its central nucleus. Although it is relatively quiet today, in the past it may have emitted powerful streams of particles, similar to those observed in active galaxies. Traces of this activity may be preserved in the structure of its halo, and in the chemical composition of stellar clusters. Observing cosmic rays is also important because they influence star formation. High-energy particles can heat the gas and prevent it from compressing. This creates a kind of feedback loop. Stars are born, leave, die, and release particles, and these particles then regulate the birth rate of new stars. In this respect, Andromeda is a perfect laboratory for studying such mechanisms. Future research on cosmic rays is connected with the development of gamma astronomy. New telescopes, such as the Cherenkov Telescope Array, CTA, will be able to measure the gamma ray spectrum with high precision and identify its sources. This will help us understand which processes in Andromeda are responsible for generating high-energy particles. Thus, cosmic rays and high-energy processes in Andromeda are a hidden layer of its dynamics. They help explain how stars, gas, and magnetic fields interact and open new ways to understand the physics of galaxies. Andromeda also plays an important role in the study of the intergalactic medium. This space, stretching between galaxies, was long thought to be empty. However, modern observations have shown that it is filled with rarefied gas, plasma, and dark matter. Due to its proximity, Andromeda has become one of the best objects for studying such processes. The intergalactic medium between Andromeda and the Milky Way is already beginning to show its influence. Studies have shown that the halos of these galaxies can partially overlap. This means that their outer layers are already interacting, even though the disks themselves are millions of light years apart. Such overlap indicates that the merging process began long before the future collision. Special attention is given to the study of hot gas in the intergalactic medium. Observations in ultraviolet and X-ray ranges have revealed a vast cloud of plasma surrounding Andromeda, which may extend for millions of light years. This gas is sparse, yet its mass is comparable to the mass of all the galaxy's stars. It acts as a connecting substance between galaxies and may serve as a source of material for future star formation. Interestingly, so-called bridges of matter are observed in the intergalactic medium. These are extended structures connecting Andromeda with its satellites and even with the Milky Way. These bridges form due to gravitational interactions and resemble hidden pathways along which matter is exchanged between systems. The hypothesis about the nature of the intergalactic medium is linked to dark matter. It is possible that dark matter forms the backbone of these bridges, while gas and plasma merely follow its distribution. If confirmed, observations of Andromeda will help clarify the distribution of dark matter across the entire local group. The intergalactic medium also serves as a cosmic archive. Within it, we can find elements ejected from galaxies billions of years ago. This includes material from supernova, stellar winds, and active galactic nuclei. In this way, the space between galaxies preserves the history of their evolution. Future observations of the intergalactic medium will be conducted using more sensitive telescopes, such as next-generation X-ray and radio observatories. They will allow us to detect fine structures and refine the scale of gas clouds. Thus, Andromeda is inseparably linked with the intergalactic medium, which plays a fundamental role in its fate. Studying these processes helps us understand not only the future collision with the Milky Way, but also the general mechanisms of the universe's evolution. Andromeda has long been an object of not only astronomical research, but also cultural interpretation. Its image appears in myths, legends, and art, combining science with imagination. This galaxy has become a symbol of infinity, mystery, and humanity's desire to look beyond the known. The name Andromeda comes from Greek mythology. Andromeda was the daughter of King Cepheus and Queen Cassiopeia. According to legend, her mother insulted the gods by claiming that her daughter's beauty surpassed that of the Nereids. As punishment, Andromeda was chained to a rock by the sea to become a victim for a sea monster. She was saved by the hero Perseus, who defeated the monster. The constellation Andromeda, in which the galaxy is located, was named in honor of this mythological figure. Over time, Andromeda became not only an astronomical symbol, but also a cultural one. In literature and art, its image is often associated with beauty, inaccessibility, and mystery. In the 20th century, its name became popular in science fiction. For example, the novel Starships of Andromeda and various adaptations inspired by its image linked the galaxy with possible civilizations, both advanced and ancient. Interestingly, the discovery of Andromeda's true nature in the 20th century coincided with a growing cultural interest in space. When it became known that it was a separate galaxy, not a nebula within the Milky Way, it turned into a symbol of the vastness of the universe. For millions of people, this was a revelation that changed their perception of space. In modern culture, Andromeda is often used as a metaphor for the future of humanity. In science fiction, it appears as a possible direction for civilization's expansion, or as a place where other forms of life might exist. Its image can be found in books, films, games, and even music. Hypotheses about civilizations in Andromeda remain mostly a cultural phenomenon, though they are loosely based on the scientific possibility of exoplanets. For many, it has become a symbol of hope that humanity is not alone in the universe. Thus, Andromeda is not only a real spiral galaxy, the nearest to us, but also an important cultural symbol. It unites mythology, science, and art, creating a bridge between ancient legends and modern discoveries. Its image reminds us that humanity's desire for knowledge is as limitless as the universe itself. Andromeda is also of immense importance for cosmology, because studying it allows scientists to test fundamental laws of nature on scales beyond our galaxy. It serves as a kind of proving ground for theories of gravity, galactic dynamics, and the evolution of the universe. If you are interested in such scientific discoveries, supporting the project with a like and subscription helps release more lectures about the mysteries of space. One of the main questions related to Andromeda remains the problem of dark matter. Its rotation curve was one of the first pieces of evidence that galaxy mass is not limited to visible stars and gas. Analysis of the motions of Andromeda's stars and satellites showed that without an invisible component, the galaxy simply could not exist in its current form. These data became an important argument in favor of cosmological models that include dark matter. Another important area is testing the laws of gravity. Some scientists suggest that anomalies in stellar motion could be explained not by dark matter, but by modifications of Newtonian mechanics. Andromeda has become one of the objects used to test such alternative hypotheses. So far, results mostly support the dark matter model, but research continues. Andromeda's fate also plays a key role in modeling the future of the universe. Its upcoming collision with the Milky Way offers a chance to observe a process that likely occurred with other galaxies. By studying this interaction, scientists refine theories of mergers, the formation of elliptical galaxies, and the redistribution of matter in space. Interestingly, Andromeda is also used to refine the value of the Hubble constant, the parameter that determines the expansion rate of the universe. Observing its motion relative to the Milky Way helps calibrate cosmological models. While the main constraints come from more distant objects, nearby galaxies like Andromeda provide important checks. Studying the distribution of stellar streams in its halo remains an important area of research. These structures allow scientists to test models of galaxy growth within the framework of cold dark matter theory. The presence of streams supports the idea that galaxies formed by accreting smaller systems. Hypotheses about future cosmological studies of Andromeda are linked to the development of gravitational wave astronomy. The eventual merger of its central black hole with the Milky Way's black hole will create a powerful signal detectable by future instruments. This will be a unique test of the laws of gravity on enormous scales. Thus, Andromeda is not only the nearest spiral galaxy, but also a fundamental object for testing cosmological models. It helps refine our understanding of gravity the nature of dark matter, and the dynamics of the universe. Studying it gives us a glimpse into the deepest mechanisms of cosmic evolution. Andromeda is a fascinating object from the perspective of future astronomical observations. It will become the first galaxy where humanity can test many hypotheses once next-generation telescopes and observational methods with unprecedented precision become available. If you are interested in following the development of space science, supporting the project with a like and subscription helps release more lectures for sleep. In the coming decades, next-generation radio telescopes, such as the Square Kilometre (SKA), will play a key role. They will allow mapping the distribution of neutral hydrogen in Andromeda with unprecedented resolution. This will make it possible to study small structures in its disk and halo that were previously inaccessible. Such data will help refine models of star formation and gas dynamics. The James Webb Space Telescope has already begun exploring individual regions of Andromeda in the infrared. Its capabilities allow us to peer into dense dust clouds and observe star formation, which was previously impossible. In the future, these observations will help clarify the history of stellar bursts and understand how intensely Andromeda evolved. High hopes are also tied to upcoming X-ray and gamma-ray observatories. They will be able to detect not only bright sources of radiation, but also fainter objects, including exotic systems and new types of bursts. For the study of compact objects in Andromeda, this will be a true breakthrough. Another area is gravitational wave astronomy. Although currently only events within our galaxy and its vicinity are detected, future detectors will become more sensitive. This will allow us to register mergers of neutron stars and black holes even in Andromeda. Thus, we will gain information about processes hidden from traditional observational methods. Equally important will be the development of methods for the direct study of exoplanets. Today, detecting planets in another galaxy seems impossible, but new technologies may make this a reality. If atmospheric signs of life in Andromeda systems are discovered, it would be the greatest scientific breakthrough in history. Hypotheses about future exploration also include the use of automated intergalactic probes. Although this idea currently sounds like science fiction, technological advances may one day allow sending microprobes to Andromeda. Such projects are being considered for the long term, over the next centuries. Thus, Andromeda remains an object of attention not only for current scientists, but also for future generations. It will become a testing ground for new technologies and theories, as well as a source of discoveries that will change our understanding of the universe. Our nearest giant neighbor combines everything that makes astronomy unique, from observing individual stars to constructing cosmological models. Studying it has been the foundation for many discoveries that transformed our understanding of the universe. And although we see it as it was 2.5 million years ago, this image allows us to build concepts of the past, present, and future of space. To ensure that such materials continue to be released, support the project with a like and subscription. This helps develop a series of lectures about the mysteries of galaxies. Andromeda shows that galaxies are not static structures, but dynamic systems, constantly changing under the influence of stellar gravity, internal processes, and interactions with neighbors. It carries the memory of past collisions, stellar streams, relic systems, and the evolution of its chemical composition. Every element, from the central black hole to the distant gas clouds, is part of a single story spanning billions of years. Particularly important is that Andromeda reflects the fate of our own galaxy. In a few billion years, the Milky Way and Andromeda will merge to form a single giant system. This event will be part of the natural cycle, demonstrating that even the largest structures obey the laws of nature. For humanity, Andromeda has become a symbol of discovery. It was from Andromeda that a new era in astronomy began, when we realized that the universe consists of countless galaxies. Today, it remains a source of inspiration for science, culture, and philosophy, reminding us of the infinity of space and that we are only a small part of the vast whole. Future research will reveal new hidden pathways of its structure. With each generation of telescopes, we will learn more about the processes taking place inside. Perhaps one day we will be able to observe exoplanets in Andromeda, detect gravitational waves from its black holes, and even create maps of its structure down to individual stars. Thus, the mystery of Andromeda is not only an astronomical object, but also a symbol of the search for truth. It shows that the universe is complex, multi-layered, and full of puzzles waiting to be solved. By studying it, we uncover not only the secrets of a distant galaxy, but also gain a deeper understanding of ourselves and our place in the universe.